Okay, so on Friday, we started our look at individual decision making. So what tools, techniques do we use as economists to model, map, analyse, describe consumer decision making? So we introduced the idea of indifference curves. So again, we don't assume too much about individual preferences. When we look at an individual, we just take their preferences as given, that the consumer does whatever it is that maximises their utility, that makes them as happy as possible. So we can have an indifference curve. So what an indifference curve represents is basically a set of consumption bundles that offer the individual the same level of utility. So in a choice between two separate goods, the individual theoretically could consume any combination of those goods. So along the horizontal axis, we've got one good, in this instance pizza. Along the vertical axis, we have another good, in this instance beer. So theoretically, the individual could consume any combination of those. So points A to F represent consumption bundles, some combination of the two goods. A certain number of units of the good in the horizontal axis, and a certain number of units of the good on the vertical axis. Because of our assumption of non-satiation, i.e. that more is better, the preference direction is up and to the right. The consumer would prefer more of both goods. And what the indifference curve shows is bundles of goods that have the same level of utility. So sets, consumption bundles, where the individual is indifferent between them. If you offer the individual either B, E, or C, the individual will be indifferent between them. Consumption bundles B, E, and C all offer the same level of utility, even though they have a different composition, even though each of them is made up of different quantities of pizza and beer. Then as you move away from the indifference curve, the utility increases or decreases whether you're moving towards or away from the origin. The origin, the point 0, 0, the bottom left-hand corner. So indifference curves closer to the origin have lower levels of utility, so D is clearly worse than E. D has lower quantities of both, whereas F is clearly better than E. F has larger quantities of both. So we can use indifference curves to track sort of any set of preferences. So if the goods are perfect substitutes, if the individual is equally willing to swap one for the other, the indifference curves are perfectly straight lines. So in general, if an individual has what we call an extreme consumption bundle, more heavily weighted towards one of the goods, the utility won't increase by as much. But with perfect substitutes, it doesn't matter. So with perfect substitutes, the slope of the indifference curve is constant. They're straight lines. Whether they have 4 cans of Coke or 4 cans of Pepsi, as long as they treat them as perfect substitutes, it doesn't matter. The utility is the same. Whether in the case of goods that aren't perfect substitutes, that might not hold. So 2 cans of each offers the same level of utility as the extremes. In general, people prefer balanced or average consumption bundles. We tend to spread our consumption across a whole range of goods. Our consumption doesn't tend to be concentrated in 1 or 2 goods. We buy a vast array of goods. So individuals prefer balanced consumption bundles rather than ones that are concentrated in one good or another. But when it comes to perfect substitutes, it doesn't really matter. One good is considered the exact substitute to the other. A second particular set of indifference curves we can consider are when goods are perfect complements, when they need to be consumed in fixed proportions. So if you have a left shoe and a right shoe, getting an extra right shoe doesn't offer you anything extra. You need to consume them in a ratio of 1 to 1. If you have 1 car and 4 tyres, well then you're at the level of utility associated with 1 car and 4 tyres. If you get 8 tyres, there's no extra utility associated with that. In order to use 8 tyres, you would need 2 cars. So the consumption needs to be in fixed ratio, whether it's 1 to 1 for left shoe, right shoe, 4 to 1 for tyres and cars. Again, we can use our indifference curves to map any set of preferences. So if an individual has a particular preference for one good or another, so over here on the left hand side, person 1, you can see that if they increase and increase substantially the quantity of good on the horizontal axis, the utility doesn't increase. So indifference curve I3 offers the same level of utility for each individual consumption bundle. So we're going from a very low level of pizza to a very high level of pizza. Yet the utility doesn't change. Utility is constant across the indifference curve. So in this instance, the individual has a very strong preference for the good on the vertical axis. If the quantity of beer increases, their utility increases. So the individual shows a preference for the good on the vertical axis, whereas in the opposite case, if indifference curves are very steep, in this instance you can see that if we take indifference curve I3 again, increasing the quantity of good on the vertical axis has little impact on utility, whereas if we increase the quantity of the good on the horizontal axis, it does. So the slope of the indifference curve can measure relative desirability. So we can use these to pick up any sets of preferences. We can incorporate these into our preferences into any set of indifference curves. And again, in this instance, we're just simplifying it. We just have two goods. And the reason you use two goods is because it's easier to show on a graph. You can then increase it and have 2, 10, 100, or any number of goods. It just moves it away from being easy to show on a diagram and requires the use of a formula or an equation. But it can be increased to any number of goods. Whether it's indifference curves then between goods that offer no utility, so a useless good, something that regardless of how much of it you have, your utility won't increase. So for indifference curve I1, the utility is entirely dependent on the quantity of pizza consumed. Regardless of what the useless good is, utility remains exactly the same. You only move to a different utility curve, indifference curve, if the quantity of pizza changes. So the useless good offers no utility, or there may be economic bads, goods where their consumption or existence reduces utility. And again, with these, having more of the economic bad reduces utility. So the preference direction is away and down to the right. In general, we look at indifference maps between two economic goods, two goods that offer positive utility. So on Friday we finished looking at a second way of tracking or mapping consumer preferences, and this is using utility. So again, it's all about preferences. What is the relative ranking of different bundles of goods? So along a utility or indifference curve, bundles of goods have the same level of utility, and then whether the indifference curve is higher or lower, you have increasing or decreasing preference. We can, in a sense, look at these relative rankings using numerical values. So if a bundle of goods are all along a same indifference curve, just give them all the same numerical value. A level of 10 when looking at utility, a level of 20 when looking at utility. And then when it comes to reducing or increasing preferences, have certain bundles of goods at higher numbers and certain bundles of goods at lower numbers. So if y is preferred to x, we could say that bundle x gives 8 utils of satisfaction and bundle y gives 10 utils of satisfaction. Now the units are entirely meaningless. There is no measurable unit of satisfaction. All we're concerned with here is the number and the relative ranking of those numbers. So if y is preferred to x, we could just apply to x 8 units of something, some concept of satisfaction, and we can apply to bundle y 10 units of satisfaction. And the numbers then tell us relative ranking. 10 is bigger than 8. We could as easily have said 8 and 10 million. The gap between them doesn't matter. All that matters is the sort of relative ranking of the numbers. So the utility function summarizes the information of indifference maps. So it takes a diagram with a whole set of indifference maps and can incorporate it into a single expression. So in our example with pizza and beer, an example of a useful utility function might be that utility, this number, is equal to the square root of the product of beer by pizza, where the numbers you put in are the units consumed. How many pints of beer were eaten, or drank, excuse me, and how many slices of pizza were eaten. So you just plug in the units consumed. What is the quantity of each? So for this utility function, you'd multiply the units by each other and then get the square root. And that will give you a utility number. So this expression represents utility function. So it just summarizes the information in an indifference map. In the indifference map, you have to show every bundle. You have to show each and every indifference curve, and you have to show a whole host of information. It could be summarized using in the utility function. Beer multiplied by pizza, and then get the square root. You can plug in for any quantity of beer. You can plug in for any quantity of pizza, multiply them together, get the square root. So as stated, utility functions don't exist in a fundamental sense. This is not like firms and profits, where we can work out a firm's profit function. Say, if you sell more, your profit will change by this amount. And it comes with a measurable quantity. We can measure profit using monetary units. We can measure profit using euro. So we can compare then across different outcomes. When it comes to individuals and consumption, we don't have the same means of measuring. We don't have something that has interpersonal comparison, that a person gets a certain quantity of utility from consuming a certain good. It doesn't work like that. So utility functions don't exist in a fundamental sense. They're not on what we base our decisions. So we may know a consumer's relative ranking of bundles, but we're unlikely to know by how much that consumer prefers one bundle to another. So the gap between the numbers doesn't necessarily matter. All that matters is knowing a consumer's relative ranking. So our measure of utility is ordinal. It's important to know the order in which bundles are preferred rather than cardinal. And cardinal simply applies to the numbers. What is the gap between the numbers? We're not too interested in the gap between the numbers. If one bundle of goods is preferred to another, it doesn't matter whether we say the utility is 8 versus 10 or 8 versus 10 million. The information presented to us is exactly the same. The bundle of goods that has the higher level of utility is preferred. So we should not put too much weight, or any weight in fact, on the absolute difference between one bundle and another. Rather, it is the relative ranking or relative utility we are interested in. So can the consumer rank or order separate bundles of goods? Since the order is all that matters, it means then that there's no definite or no single utility function, whereas a firm has a single profit function. If it makes more, this is what will happen to it. For individuals, we don't have a single utility function because it's the order that matters. So what happens with utility functions is that you can undertake what's called a monotonic transformation. And that simply means you don't change the ordering. So since only the rankings matter, there can be no unique way to assign utilities to bundles of goods. So a monotonic transformation is a way of transforming one set of numbers into the other that preserves the order of the numbers. So if you have two numbers, 4 and 6, if you multiply them by a positive number, the order doesn't change. 3 times 4 is 12, 3 times 6 is 18. So whether you rank 4 versus 6 or 12 versus 18, the outcome is exactly the same. If you did that for a firm, if you took their profit function and multiplied it by 3 and said, sure, it's only the order that matters, well, then clearly your profit function would be entirely skewed. You'd be telling the firm they could make 3 times more profit, when in fact they couldn't. All you've done is multiply their profit function by 3. When it comes to utility, you can do that because the relative numbers don't matter. It's just the order. So you could add any number. So again, take 4 and 6. If you added 3 to them, whether you dealt with 7 and 9 or 4 and 6, it doesn't matter. Or you could raise it to a power. So if you took 4 and 6, and if you cube them, so 4 cubed is 64, and 6 cubed is 216. So again, when you deal with 4 and 6, or 64 and 216, the order stays exactly the same. So there's no unique utility function. So we don't have sort of individual or personal utility functions. We just need something that ranks or orders goods. So if a person rates or ranks a particular set of goods in a particular order, the utility function just has to satisfy that. The numbers don't really matter. So a monotonic transformation of a utility function is a utility function that represents the same preferences as the original utility function. So if this down here is a utility function we're going to use, we could multiply it by 3. We could add 3 to it. We could get the cube of it. As long as the order stays the same, the utility function is useful. One issue we can look at with utility functions that may not be as sort of obvious with indifference curve is the concept of marginal utility. So you remember back at the start, one of our basic principles of economics was that decisions are made at the margin. If you're looking to consume the next unit of a good, it doesn't matter what the previous 5 offered in terms of utility. What matters is how much utility will you get from the next, how much utility will you get from the 6th unit if you're going to buy and purchase the good again. After purchasing 5, that's in the past. You might look at it as sort of a guide of information or a pick-up of an experience. But when making the decision, the person will say, well, how much utility will I get from the next unit? So as a person consumes more of a good, utility increases. The important issue is, well, how much more does it increase by? Is it worth purchasing the next unit given whatever the increase in utility will be? So somebody gets up in the morning and has the first cup of coffee. 10 o'clock they have the second. 11:30 they have the third. By the time they get to 1 o'clock and they're having the fourth, is it having the same impact? Are they going to continue to consume at the same rate right throughout the day? Or are they looking for a kick early in the morning and then have a sort of a less strong effect later in the day? So the marginal utility or the marginal benefit is what guides our decisions. It's not average utility or past utility. It's the utility of the next unit. So the margin is the next. So the extra utility, so delta U, what is the change in utility? So that's the Greek symbol delta, just reflects change. So the extra utility that a person gets from consuming the last unit of a good is the marginal utility. So MU, marginal utility, is the change in utility for a change in quantity. So if quantity changes by 1 unit, what happened to utility? How much did it rise by? So marginal utility is simply the change in utility for a 1 unit change in quantity. Or in other terms, it's the slope of the total utility function. How quickly is utility rising? Is it rising very steeply, or is it rising very flat? What is the impact in utility of consuming 1 extra unit? So the marginal utility of any quantity is the first derivative of the utility function. When it comes to functions, the slope is simply the first derivative. What is the rate of change? So the slope reflects the rate of change. So when looking at total utility, we narrow it down to 1 good. So unlike with indifference curves, where we had goods on the horizontal and vertical axis, here on the horizontal axis, we have quantity. How many units of the good do you consume? 1, 2, 3, 4, 5, 6. And then up along the vertical axis, you have total utility. How much extra utility do you get? And it's the slope or shape of the utility function that matters. The actual numbers aren't that important. We could multiply all those numbers by 10 and we get the same slope, the same shape. But what matters is the rate of increase. So that, for example, this could be a utility function. Utility is equal to 10 times the square root of x. It could as easily be utility is equal to the square root of x. Or utility is 100 times the square root of x. Just something that gives us the same order. So in this instance, if you look at point A and look at the slope, The slope shows you how quickly utility is rising. So utility rises quite rapidly at first. So the first cup of coffee in the morning has a substantial kick for the individual. As you work through the day and the individual consumes more and more, the extra or marginal benefit is getting smaller and smaller. So if you look at point C, the slope is beginning to flatten off, or sorry, point B, the slope is beginning to flatten off. And if you move on to point C, the slope will be even flatter again. So the extra or marginal benefit is declining. And in fact, if we were to graph the marginal utility, so what is the slope of the total utility function at units 1, 2, 3, 4, 5, 6, the slope declines. The utility function is getting flatter and flatter. So consuming more and more units of a good does increase utility. So the more consumption, utility increases. The key issue is that utility increases at a decreasing rate. So our marginal utility begins to decline. So the slope gets flatter and flatter. Our marginal utility begins to decline. So at point A, the marginal utility is 5. The slope is quite steep. By the time you get to C, the slope is 2.25. It's beginning to level off or flatten. So how can we tie in these two different approaches to measuring individual preferences? Are they entirely separate? Is the indifference curve approach one way of doing it? And is the utility function approach a second way of doing it? And is there any link between them? Is one just based on a graph where you draw lines and say utility is the same along all those points in the line? And is the second one based on a function? Just get me a number and I'll compare the number whether it's higher or lower. In fact, they're quite related, that you can transform or transfer one into the other. That if you have the utility function, you can draw the indifference curves. And if you have the indifference curves, you can get the utility function. So they are the same way of dealing, or sorry, they are different ways of dealing with the same concept of preferences. So we'll consider an individual utility function where utility just depends on the consumption of two goods. So utility is equal to the utility the person gets from X and Y. X being the quantity of X, Y being the quantity of Y. Whatever those quantities are, whether they're beer and pizza, Coke and Pepsi, left shoes and right shoes. So the individual's utility depends on the consumption and the units consumed, more particularly, of those two goods. So X and Y will represent the units, the quantity. So if you just let MUX be the marginal utility from consumption of good X, and then MUY be the same for good Y. So formally, MUX is just a partial derivative utility with respect to X holding Y constant. What does that mean? Partial derivative. Well, if I consume more X, so leave good Y the same. That's at 5 units, whatever that is. Just leave that constant. Let's increase the consumption of good X by 1 unit. So this is why it's called a partial derivative. You're just changing one of the variables. You're not changing the consumption of X and Y. If you did that, it'd be hard to isolate the impact of one good or the other. When you change X and Y, utility is going to change. But which good actually caused it to change? If you change both of them, you can't isolate the individual effect. So what you mean by a partial derivative is just change one of them. Allow the consumption of X to increase while holding the consumption of Y constant. So the marginal utility of X is the derivative, or the partial derivative of a utility function. So U, depending on X and Y, with respect to X. So what is the change in utility for a change in the consumption of X? So just like the indifference curve, we'll say there's a set of bundles of goods that give the consumer a given level of utility. So some number, that number could be 10. And there are a whole host of bundles of goods out there that allow the individual to have a utility level of 10. So it could be a lot of one good and very little of another. It could be average amounts of both goods, or it could be a lot of the other good and very little of another. But each of them gives a set or fixed level of utility. So U bar just indicates that utility doesn't change. It's just some number. Utility doesn't change. And that, in a sense, is the expression for an indifference curve. Along an indifference curve, utility doesn't change. So this is the equation for an indifference curve with utility u bar. Just some number, just fixed, some fixed level of utility of utility. So the slope of the indifference curve is found by determining the changes in x and y that leave utility unchanged. So if you move to a different point on the indifference curve, the utility remains exactly the same. So if you move to a different point in the indifference curve, the quantity of x and y has changed. But what hasn't changed has been the overall level of utility. So if x rises, y must fall. The slope gives the rate of change. Does the individual have a preference for one good over the other? Is it a case where the individual prefers an average level of utility? So if we differentiate this expression for the indifference curve, u bar, and set it equal to 0. Setting it equal to 0 means utility doesn't change. So d u bar, what is the change in utility? Well, along the indifference curve, it's 0. And that's all really we're concerned with. So if you look at what it means, it's the marginal utility of x multiplied by the change in x. So dx is just the change in x. How many extra units of good x do you consume? Plus the marginal utility of y multiplied by the change in y. Along an indifference curve, that has to equal 0. If you consume more of one good and utility rises, you must consume less of the other good, so utility falls. And the key to be along an indifference curve is that the change in utility is 0. That is the indifference curve. The consumer is indifferent between consuming different bundles of goods along the indifference curve. That's the basis of them. So if we increase one of the goods, we must reduce the other. Otherwise, we can't stay in the same utility function. So because marginal utility is positive, if you consume more of a good, you get more utility. So because marginal utility is positive, it must be either that the change in x is negative or the change in y is negative. To stay along the indifference curve, if you increase one, you must reduce the other. So rearranging terms from the previous expression just gives the following: dy dx, the change in each good, is equal to the negative of the ratio of the marginal utilities, negative mu x over mu y. And given that dy dx is simply the slope of the indifference curve, and on Friday we looked at what was the slope of the indifference curve. Well, it's how likely or how willing is the person willing to give up 1 unit of one good in response or in exchange for a certain number of units of the other good. So dy dx represents the change in units, and mux over muy represents the change, or the ratio, of marginal utilities. So what determines how likely somebody is willing to give up 1 unit of a good? It's the marginal utility. If the marginal utility of one good is very high and the marginal utility of the other good is very low, if I give up 1 unit of the good with a very high marginal utility, I must get an awful lot of the good with a very low marginal utility to keep me at the same level of utility. If I get great satisfaction from one good, I'm unwilling to give it up. If the marginal utility is quite high, if then I'm to be compensated by something I don't really enjoy that much, I must get a lot of it. So the marginal rate of substitution, the willingness of the person to swap one good for the other, how willing is the person to give up units of y in order to get units of x, is determined by the marginal utility. Simply determined by the enjoyment or satisfaction the individual gets from consuming goods. So the MRS, the marginal rate of substitution, the willingness of the person to swap one good for another, is the negative of the ratio of the marginal utility from one good to the marginal utility of the other. So it could be x and y, pizza and beer, whatever 2 goods you wish to change. That's just a second way of proving it. So to maintain utility, if you get more of one good, you must have to get less of the other. So thus the marginal rate of substitution is negative. And just like the utility functions, so the slope of the indifference curve and the slope of the utility function are related. But just like the utility functions are not uniquely determined, the marginal utility functions are also not uniquely determined. They can also be monotonically transformed. The numbers don't matter that much. Again, what matters is relative change. So if you have MUX over MUY, or 3 times MUX over 3 times MUY, the 3's will cancel off. The 3 above the line will cancel with the 3 below the line. So the ratio remains exactly the same. So if it's 100 for one good versus 1,000 for another good, ratio of 10 to 1. Or if it's 100,000 for one good versus 1,000,000 for the other good, it's still a ratio of 10 to 1. The ratio stays exactly the same. So if you perform a monotonic transformation, multiply a number, add a number, you're not changing the ratio of the marginal utility. You're not changing the strength of preference. You're just changing the numbers. So the numbers don't matter a whole pile. Different types of utility functions we're not going to consider in any great detail. We are going to look at one example. So there's 4 types of utility functions there. The one we're just going to look at is the one that's used most frequently, and it's called the Cobb-Douglas utility function. Cobb and Douglas being 2 economists back in the US in the 1920s who sort of experimented with different functional forms. How can you put a utility function together? How should you combine, say, the production or consumption of goods into a mathematical equation? So they were the first to use this form here. They primarily used it for production. They were looking at production functions, but it's equally as applicable for utility functions. With production functions, the number clearly matters. With production functions, the goods they were looking at were inputs. What were the inputs into the production function? So if you had a certain amount of human capital, a certain amount of raw material, a certain amount of machinery, how much could you produce? And they use this form of production function to track that. So clearly the number matters. When it comes to applying it for utility, the number isn't as important. So if you say, look, you can produce 100,000 units of your good with these inputs, well, that clearly is information for the firm. When it comes to utility, the actual number doesn't matter, but it does give the ordering. So suppose an individual has the following Cobb-Douglas utility function. So as before, utility depends on the consumption of X and Y. So where X and Y are the units to be consumed, the quantity of X and the quantity of Y. In this instance, rather just than assuming a generic functional form, with the Cobb-Douglas we put a specific functional form on it. So utility is dependent on X and Y. It doesn't tell us how utility is dependent on X and Y. It just tells us that it is. So this is the Cobb-Douglas form here. So X and Y are the units. How much X do you consume? How much Y do you consume? A, alpha, and beta are just parameters. They'll just be numbers. So we'll look at an example where we input and apply numbers. So A, alpha, and beta are just parameters. They define the relationship. What is the level of utility? So if you consume more of X, what happens to utility? Well, it depends on A and alpha. If you consume more of Y, what happens to utility? It depends on beta. So looking at the Cobb-Douglas production function, we can begin to make certain findings about utility. So when it comes to marginal utility of consuming good X, it depends on alpha. So if you increase consumption of X, the marginal utility depends on alpha and the quantity of X you've consumed. So how much X have you actually consumed? And you can see that because X is below the line, the more and more of X you consume, the lower, the smaller and smaller the marginal utility will be. And the same then holds for Y. What is the marginal utility of Y? Well, it's related to beta and the amount of Y you've consumed. So let's just put numbers on these parameters. So A, alpha, and beta just means they can have any numbers in there. So let's just impose or use numbers which might be useful. So we'll let alpha equal to beta equal to 1/2. And we let A equal to 20. So in this instance, rather than just having utility is equal to A x to the alpha y to the beta, what we're actually writing is in specific form, utility is equal to 20 x to the power of 1/2 y to the power of 1/2. We're imposing or saying this is the utility function. So you can go and estimate values, find values, guesstimate values to impose or set into the utility function. So what is the utility for different consumption bundles? So if the individual consumes 4 units of each good, how much utility do they get? So if they consume 4 units of each good, x is equal to 4 and y is equal to 4. Now all we have is a set of numbers. Everything is in fact a number. There is no unknowns. We know what A is, we know what alpha is, we know what beta is, and now we've assumed x and y. So rather than having this sort of generic construction here, utility is equal to whatever happens in here, we can say the utility where you consume 4 units of x and 4 units of y is 20 times 4 to the 1/2 multiplied by 4 to the 1/2. So 1/2 simply means square root. So square root of 4 is 2. The square root of 4 is 2. So that's 20 by 2 is 40. By 2 again is equal to 80. So we can state that the individual derives 80 utils of consumption from a bundle that comprises 4 units of each good. So again, the important issue is ordinal ranking. Saying somebody gets 80 utils of satisfaction from having 4 units of each good, 4 pints of beer, 4 slices of pizza, is largely meaningless. What can we do with that information? Very, very little. The important information comes when we look at, well, what are the rates of change at that position and how does it compare to other consumption bundles? So the marginal utilities are given by alpha times utility function divided by x, and the marginal utility of y is beta times utility function divided by y. So what is the marginal utility of x when I'm consuming 4 units of x and also consuming 4 units of y? Well, alpha is 1/2. We know that the overall level of utility is 80, and I'm consuming 4 units of x. So it's 1/2 times 20, and 1/2 of 20 is 10. And the same holds for the marginal utility of y. So if I'm consuming 4 units of x and 4 units of y, the marginal utility of y is 10. So in fact, the marginal utility of both at 4 is the same. They both offer the same level of utility. However, if we look at a different consumption bundle, so 4 is a very balanced consumption bundle. It's equal units of each. What about a consumption bundle that's unbalanced, where there is 2 units of x and 8 units of y? So in this instance, there's 10 units in total. The person now is consuming more goods. 4 units of x and 4 units of y is 8 units in total. Here it's 2x and 8y. In this instance, if you plug 2 and 8 into the into the utility function, so rather than having 4 and 4, if you put in 20 times 2 to the 1/2 and 8 times to the 1/2, you again get utility of 80. So even with more goods, the person is still having the same level of utility. Well, why is that? Well, now their consumption bundle isn't as balanced. They've got fewer amounts of one good, and they're very heavily concentrated or weighted towards the other. So the total level of utility is 80. This means we're on the same indifference curve. Consumption bundle of 4, 80 units of utility. Consumption bundle of 2, 8, 80 units of utility. We're on the same indifference curve. Now look at what happened to the marginal utility. How have the marginal utilities changed in this instance? So for the marginal utility of x, in this instance we're dividing by 8. So it becomes 80 divided by 8, which is 10, multiplied by a half, which is 5, and the other way around. And the marginal utility of y. So in this instance, the individual isn't getting equal satisfaction from both goods. In this instance, the person wants more of the good they're consuming less of. So they only have 2 units of x. If you give them an extra unit of x, the utility increases by 20 units. Because they're only at 2 units, they're quite low. They've only had 2 cups of coffee. The third one will still give them a major kick. If it's good y, if good y is, say, bottles of Lucozade and they're on to the 9th one for the day, it's unlikely to have a big effect. They're already full of sugar as it is. So going from 8 to 9 has a much smaller effect in utility. So the marginal utility of y is much smaller. So in this instance, the person would prefer more x. Of course, we have to consider the price, which is what we have to add. But if it just comes down to a utility choice, x, because they're consuming less of it, has a higher marginal utility than y. So the marginal utility of x is greater, the fewer units being consumed. So with x equal to 4, marginal utility was 10. But with x equal to 2, marginal utility is 20. So we can use these points to show how utility changes along an indifference curve, given that utility is constant. So utility will be 80 units. So the slope of the individual's indifference curve is given by the marginal rate of substitution. How willing are they to give it up 1 unit of one good for 1 unit of the other? So if they swap 1 unit of one for a unit of the other, it's dependent on the marginal utility. If I give up a slice of pizza, how much extra utility will I get from an extra unit pint of beer? You're only willing to swap if the utility stays the same. So the slope of the indifference curve differs with x and y. So when I'm heavily consuming x, 8 versus 2, the person would actually give up 4 units of x for an extra unit of y, because their consumption bundle is relatively unbalanced. The marginal utility of getting this 8 unit was quite low. They already consumed 7. What was the extra gain from going to 8? Whereas if this goes from 2 to 3, the gain will be quite high. So in fact, the person would be willing to give up 4 units of x for an extra unit of y. If the consumption bundle was balanced, 4 units of each, the willingness to swap is much lower. They swap on a 1-for-1 basis if the consumption bundle was quite balanced. Whereas if the individual was consuming a very small amount of x, only 2 units, and you said to them, how much x are you willing to give up for an extra unit of y? Well, in that instance, they'd only be willing to give up a 1/4 unit of x. They're already down to 2. They don't want to give up much more. In fact, if they got an extra unit of y, they'd only give up a 1/4 unit of x. So the marginal rate of substitution diminishes as we move along the indifference curve. As you give the person more and more of one good, they're willing to give up more and more of that good to get back to the balanced consumption path. So indifference curves and utility functions are sort of 2 sides of the same coin. Do you want to draw it graphically and track to see which indifference curves are further from the origin? Or do you want to do it numerically? Do you want to put a numerical value on the consumption bundle, where the consumption bundle that has the highest utility is the one that's preferred more? The one addition we get from using utility functions is the concept of marginal utility. And it's marginal utility that drives consumer choices. So what we need to add is clearly constraints. This is what the person wants to do. What's equally important is what the person can do. And to do that, we must look at money, income, and prices. So we'll leave it at that for today and take it up with the budget constraint on Friday.